Can I stop it here, or I might have to go for one more level of page table? Definitely I need to go for one more level of page table, because this level of page table is not accommodated in a single frame. It is accommodated across multiple frames. So I might have to go for one more level of page table. Fine. Now how many entries do I need here? I need a total of 2 power 8 entries, right? Because I have a total of 2 power 8 pages over here, and I will maintain a single entry for every page in this level of page table, and so I will have a total of 2 power 8 entries. Now tell me, how many pages do I need? I need to maintain a total of 2 power 8 entries over here, but a single page can accommodate 2 power 18 entries, right, which is bigger. So single page is more than enough. In fact, see, all these page sizes are same, right? Don't get confused. I'm just drawing it. Fine. So here I can accommodate a total of 2 power 18 entries, but I need only 2 power 8 entries, 0, 1 and so on up to 2 power 8 minus 1. I am accommodating only 2 power 8 entries, and the remaining space is actually getting wasted, right? I cannot utilize this space. So clearly there is internal fragmentation over here, right? Clearly there is internal fragmentation. Now can I stop it here, or should I go for one more level of page table? I can definitely stop it here. Why? Because this complete level of page table I am able to accommodate in a single frame. So I can stop it here, because I can index into those entries using simple addition. You know how it happens, right? Anyway, let's see that later. We have seen it already a lot of times. Fine. Now this is how this level of page table holds. Now what is the total size of this page table here? See, here the complete page is actually occupied with entries. So what I did was number of pages into size of a single page. But here I cannot do that, right? Because I am not occupying this page. This space is not accommodated for page table, right? They are asking what is the size of the page table. So what I need to do is number of entries into size of a single entry will actually say the total space which I am giving it for page table entries in this level, right? We have a total of 2 power 8 entries, fine, and size of a single entry is nothing but 4 bytes. I am writing it as 2 power 2 bytes. So 2 power 8 into 2 power 2 is nothing but 2 power 10 bytes. This is the total size of the page table. I am going to maintain it over here. Fine. So this is how the page tables are created. Now how many levels of page tables are created? See, this is process, okay? Don't count this as levels of page table. This is our actual process, pages of process. This is one level of page table. This is another level of page table. This is the third level of page table. So I'm maintaining a total of 3 levels of page tables, right? I'm maintaining a total of 3 levels of page table. Now how they all will be connected, as you know, right? This will hold a pointer over here, this will hold a pointer over here, and so on. It will keep on pointing it. Similarly, this level will keep on holding pointers, right? That is how it will be present. Similarly, this will hold process, right? You know all these things. Now the question is, how many regions will our page number field will be split into? See, you know that our CPU will generate logical address, and we will have something called as page table base address of this page table, right? Using this address, page table base address, I will be able to reach the starting address of this page table. Fine. Now after reaching it here, I will use one region. See, this will be divided into regions. Now I will use one of the outermost region. I will index into this page table, right? After this, I will using the frame number I get from here, I will go to one of the pages. Again, I will index it over here. Likewise, it will keep on happening, right? We have seen it already. Now my question is, see, once I reach using this page number field, this complete field, I need to end up with one of the pages of our process, right? Once I reach one of the pages of our process, I will use the page offset field, and I will pick one of the bytes within the process, within the page of process, right? That is simple. Now my question is, see, now we need to use this page number field and index into 3 levels of page table, right? I need to index into 3 levels of page table. So this page number field will be split into 3 regions, right? this page table will definitely be split into 3 regions. Now what is the size of it? We will see that now. Now my question is, what is the size of this region? What is the size of this region? See, this region is actually used to index into the outermost page table, right? This region is used in order to index into this level of page table. Similarly, this region is used in order to index into this level of page table. Now my question is, what will be the size of this region? How many bits will this region hold? That really depends on how many entries are present in a single page in this level, right? Because I will end up with one of the pages over here, right? When I'm coming from there, I will end up in one of the pages, either this page or this page or this page or whatever, but I will end up in only one page. Now after reaching this page, I need to pick one among these 248 entries, right? 218 entries. We have a total of 218 entries. I need to pick one among these 218 entries in order to know the frame number through which I will be able to reach one of the pages of process, right? So I need to pick one among these 218 entries. I don't know which page it is. So in order to pick one entry among 218 entries, I need a total of 18 bits, right? I need to denote the address. I need to denote the entry number using 18 bits because I have a total of 2 power 18 entries. So what I will do is I will maintain a total of 18 bits in this region. Okay, this region will have 18 bits. Fine. Now how many bits will this region hold? That again depends on how many entries a single page is actually holding, right? A single page actually holds 2 power 18 entries again. The same, right? Because again in this page table also, in this pages also, I am going to completely accommodate the page table entries. So I need a total of 18 entries over here as well, right? Now how many bits will I need here? One thing I can do is the total size is 64 minus 20 minus 64 minus 20 minus 18 minus 18. I can compute it this value, right? From 64, in case if I reduce 20, it is 44, fine. Now from 44, in case if I reduce 18, it is going to be 26, fine. Now from 26, in case if I reduce this 18, it is going to be just 8. So the answer for this is 8, right? So that way I can compute it, or I can compute it in another way. See, this region is actually used in order to index into this level of page table, right? So among this 2 power 8 entries, I need to pick exactly one entry, right? That is the job of this region. Now in order to pick one entry among 2 power 8 entries, I need a total of 8 bits, right? So we can also compute it this way. Anyway, either way is fine. So anyway, this region will hold a total of 8 bits. Now in case if you add all 4 of them, all 4 numbers, you will get 64, right? 18 plus 18 is 36, 36 plus 8 is 44, 44 plus 20 is 64, right? So this is how our address split will look like. Okay, this is how our address split will look like. Mind you, this is page number field. Okay, this is page number field and this is page offset field. Don't get confused here. Okay, our page number field is split into 3 regions because we have a total of 3 levels of page table. So we have computed all these things, right? We have computed the address split. How the address split will look like? It will look exactly like this, which means I have a total of 64 bits where page number field is going to hold 44 bits and page offset field is going to hold 20 bits. And again the page number field is split in this way, right? This is what we have computed. We have computed the address split field, address split, fine. Now what is this maximum number of page table entries in a single page? What is the maximum number of entries I can place in a single page? It is 2 power 18, right? See, don't say this is 2 power 8. Here we are not actually accommodating the maximum level, right? I am just occupying few entries and I am leaving this space because I don't need it. Now the question asked is, among all these things, what is the maximum number of entries I can accommodate in a single page, right? In a single page, I can accommodate a maximum of 2 power 18 entries, right? 2 power 18 entries. So the answer for this is 2 power 18 entries. Fine. This is what we have computed all the values, right? Now one question I want to ask you here is, how many memory accesses I need in order to get a single byte for the CPU, right? See, CPU will access a single byte, right? Now in this example, how many times I need to access the memory in order to get the single byte. That is very important, right? See here. Our CPU will initially generate the logical address, fine. Now once it gets the page table entry, page table base address, it will reach this level of memory and it will index into this level using this field, right? Using this region, fine. So using this region, it will index into this level, fine. Now after indexing into this level, it will get the frame number, and again this is one memory access, right? This is also present in memory. So I have a total of one memory access so far, fine. Now after getting the frame number, I will again access one among these pages, and that will cost me one more memory access, right? Now after getting the frame number over here, again I will access memory once in this level, right? So one more memory access. Now after getting the frame number over here, I will go into the page, or I will go into the process, and I will fetch the byte, right? So for that it will take one more memory access. So I need a total of 4 memory accesses in order to access I need 4 memory accesses in order to fetch a single byte. Coming to this problem, right? Which means I have a total of 3 levels of page table. So for every level of page table, I need 1 memory access. So since I have 3 levels of page tables, I need 3 memory accesses, plus I need 1 more memory access in order to access the process, right? Pages of our process. So I need a total of 4 memory accesses. Now one more very important point you need to know, very important formula you need to understand here is, in case if I have n levels of paging, okay, here we have 3 levels of paging, right? Now in case if I have n levels of paging, then the number of memory accesses in order to access a single byte of our RAM is nothing but n plus 1. Okay, what do I mean by this? In case if I have n levels of paging, here I have 3 levels of paging, I need a total of n plus 1 memory accesses in order to fetch a single byte in the RAM. Here I am going to fetch a single byte, right? So I have used here 4 memory accesses. Now how I got this n plus 1? In case if I have n levels of paging, I need n memory accesses for n levels of page tables, and I need one more memory access for accessing the process. So n plus 1 is nothing but n plus 1. We have computed it, right? So this is what you need to understand. Now my question is, as we keep on increasing the number of levels of paging, will the time taken to fetch a byte increase or decrease? Okay, see, you need to understand this. In case if I don't have paging, okay, let us assume that I am not using paging, which means I am going for contiguous allocation. Now what will happen? I don't need to access all these page tables, right? I will go into the process directly by using simple addition, and I will get the byte. So I need only one memory access. Why this happened? Because I had a total of 0 page tables, 0 levels of page tables, and I got a total of 1 memory access, right, in order to access a single byte within the process. Now in case if I am using single level page table, what do I mean by single level page table? I will have the process and I will have only one level of page table, which means in this level of page table, I will be able to accommodate the complete page table within a single frame, right? In that case, we don't go for multiple levels of paging. We will stop with only one level of paging. In that case, I have a total of one level of page table, and so I need a total of 2 memory accesses. Why 2 memory accesses? One memory access for one level of page table and another memory access for the process. So I need a total of 2 memory accesses. Now in case if I have a total of in case if I have 2 levels of page table, then I need 3 memory accesses. So one thing you can understand from this is, as the number of levels of page tables keep on increasing, the time taken to access a byte will also increase, or the number of memory accesses in order to access a byte of a process will also increase, right? See, what I want to tell you is, as you keep on increasing the number of levels of page table, the time taken to access a single byte in our RAM or single byte of our process will actually increase, right? So we should understand that we should keep the number of levels of page tables as less as possible, considering the memory access time criteria, right? Anyway, Coming to memory access, we are going to see another concept, right? We have a big topic named memory access. We are going to see a lot of problems there. So in case if you didn't understand the last point I told you, it is fine. Okay, we will see about memory access later.